Um, I I'm going to talk about hacking your RC car, which I've been working on for uh, a month and a little over a month or more, and I'm working on a project for Robo Games using this RC car from Traxxas. And for Robo Games is next week in Northern California. By the way, my name is Jim D'Annunzio. I'm a software engineer, career software engineer. I work for Samsung TV video display division for Samsung Research America. And I got into robotics with this club in around 2015 and watched many lectures, attended, and then started building my own within a couple of years. And so now I'm like vice president. And I wanted to participate in competitions when I could. And so I went up to Robo Games last year in Northern Cal, it was Pleasanton, in the Bay Area. And Robo Games is a big event. It hadn't occurred since 2018 prior to that, and it's occurring again this year in San Jose Convention Center. It's a $60 to attend it per day. It's a little pricey, but if you enter a robot, it's $85 for the whole weekend for all the days. So I'm entering a couple robots. This one is called Robo Magellan. I'm not sure it's gonna be ready in time, but Robo Magellan is a contest where you use a GPS and on your robot, and it's outdoors, and it has to navigate to this destination traffic cone all on its own, autonomously. So that is like the goal, and a few of us here are working on that. So with that, I'll start introducing what I did initially, and several other people here have done this before. And on the internet, a lot of people have taken these RC cars as a base and turned them into autonomous vehicles. And I'll show you why that is a convenient thing to do. It's a little, it's a little pricey. These run $370, or I always buy things on Black Friday, so you're going to get some discount. But there's various prices for these cars. But as a robot platform, so much is already there for you. The motors, the wheels, the suspension, everything is remote control, and they are surprisingly relatively easy to turn into an autonomous vehicle because of the standards they use. So this is what the original looks like. By the way, mine is over there. You'll see pictures of it online here as we go. But that's the physical robot. So this is what it looked like when I got it. You can see there's, I guess I should use the mouse here. You see there's some, I'm going to be putting on electronics into this device. So I need some space. And so you see there's some flat areas here, and that's what I end up using. This is the ESC, electronic speed control, and the motor. This is a single motor that drives all four wheels. This is a four-wheel drive car. And through linkage, the single motor drives all four wheels. The battery goes in this little spot here. The electronic speed control is what handles the motor. And over here, you can't see it's covered, but this is the receiver for the remote control, 2.4 gigahertz remote control. That drives the steering and the motor. And we'll see how we're going to hack both of those. Here's another view of the car. So of the untouched car. So now,
oh, Jim.
Yeah, and
one cool thing about the name Traxxas is the brand name is that the quality is pretty decent for stock vehicles. So I've used a bunch of these.
Have you?
A lot of them, yeah. So this is a good, good choice. So.
Right, and they're pretty sturdy, and every hobby store has parts of you.
Yeah.
Like a liquid charm, you go down the street, pick it up for $5 and drop it moving again, instead of mail
You
ordering.
you
And
can change everything to aluminum, by the way. Go on Amazon, every piece you see there, you can change it to the aluminum if you want.
Oh, the whole
Everything,
frame?
anything that you see.
Wow. Yeah, so there's a lot of support for these because
A lot of it.
there's potentially, well, I don't know, a million people out there who like to use their RC cars. This one's a crawler. It's not designed for speed, but to go over rough terrain. And that's partly why I bought it, because of the potential in Robo Magellan could be over grass and sometimes you go over a curb without even realizing it because you're using GPS coordinates, etc. And it can go slow, which is another kind of recommendation I got for a Robo Magellan is you want to be able to go slow when you need because a lot of RC cars, they are designed very fast and it's a hairline trigger and it will just go off so fast. So that was the recommendation. But other people, you can use the faster cars. You just have to be a little more, aware of that. So, so here's the beginning of some of the hardware changes I've made. I guess, yeah, I'll show you piece by piece, but so a microcontroller is necessary to take over control instead of the receiver just sending the pulses from your remote control. You want to control them via a microcontroller. So this is a Teensy 4.1 in a 3D printed case. And as I said here, this is the, I have another picture of it uncovered. This is the, where the receiver is and the, where the servos plug in the original card. Both the steering and the drive motor plugs into this, so I'm kind of hacking into that. On the right here is an IMU, MPU, inertial measuring. So that gives the acceleration. It's a 9-degree accelerometer, and a gyroscope and a compass. That is to help know where the car is and what its orientation is, and that plugs into the Teensy as well. Over here you have the GPS module, which is we'll get into that later. That's going to be how I know where I am outdoors. And then of course the main brain is Raspberry Pi 4B here. And now I'm skipping over, but I had to figure out a way to mount these, and luckily on these cars there's sort of unused screws. You can see here there's these screws that keep this cover on, but there are other ones that are unused. And if you take off some part, like I took off a part, this railing here is removable by these 4 screws. So I didn't really need this. I mean, it's helpful to keep your robot in real rough terrain from damage, but I decided, for Robo Magellan, I'm not expecting that level of rock climbing. So I took this off and I was able to use these mount points to mount electronics on that side anyway. And then this Teensy kind of just wedges in there. It's not even screwed down, but these other ones are screwed down. And that's what it's nice to make a case out of a 3D printed case. And I'll show you a lot of these are downloadable, or these are all downloadable, these cases. And then I modified them to fit my needs. So the Raspberry Pi is there. That's the main brain. And using USB connections, power the other, the Teensy comes off, it's powered by USB. As well as other things. Actually, the GPSs as well. Now here is where I needed my own power supply for the electronics. I did not tap into the the main battery, which is an option. Some people do it. The main battery, if you do a little more advanced work and get a splitter and a buck converter, then you could do that. In the time I had, I decided I'm very used to these power banks. So I installed a tray in the back and have this power bank that has 5 volts. And that keeps that powers the Raspberry Pi and some of the other electronics conveniently with a separate power supply. Now, like on the underside of the top frame, you'll see it's a little bit of a mess of like long cable. I didn't have time to really cut these cables, but if you secure them all, you with tape and whatever, you can kind of manage this. So, because I need to take the top off to replace the battery, to charge it, and to press the main button to turn things on, to turn on at least the main power for the ESC, which is here. You have to press this little button to turn on the motors of the robot. But for my electronic control, you just like kind of lift the back and there's a button here that turns on the power bank. So that part, we don't have to lift too much. And the other thing I did was install a bumper. This is a sensor that if I hit something, I'll get feedback, and that goes into the TC as well. This bumper I got from DF Robot. It was part of my Big Orange project, but you can buy, I think DF Robot may still have those. And that's just a way to know if you've hit something, and then you can, it's the last resort of obstacle avoidance. The other thing I did, so going through all the mechanical stuff first, obviously, or in a mix of electronics. So here's some more mechanical things. I needed, on the front of the robot is there's a camera and a mount of a pan tilt mount. And I guess didn't show a picture of that. This is what it looks, this is what the whole robot looks like. And so you've got a LiDAR mapping system on top and this OPD camera on the front, and it's got a pan tilt servo as well there. And so to do the cabling, I drilled a hole and had these little gasket rubber grommet, yeah. And I just thought I got to use that. It's perfect. It will keep the things from, keep the cables safe. And it was just big enough to put through a USB-A connector through that, or a Ethernet RJ6 or an RJ whatever connector. And then here's the one in the back, and I immediately put them in the windows of the car, so they're kind of, I like an aesthetic appeal to not wreck it too much. So that's that part. Another important thing that I got into for this project is a DuPont crimper. I've been, for whatever, 6 years, I've been using standard length DuPont cables that you just buy. And by the way, the DuPonts are what you see here, all those wires here are DuPont. But they come in different lengths that you buy, and they could be too long or too short. So finally, I'm like, yeah, I want it very clean in there. There's not much room. So I bought this and learned how to crimp. And my first few, you kind of mess them up and you throw them out, and you have to test every single one you make to make sure it's like, I made a couple and it's like looks perfect on the outside and there's no continuity. It doesn't actually connect. So anyway, but
that's pretty high on my list of things I hate to do. I have all the gear and about 80% success rate with it.
Yeah, I just started, but I assumed I would have some mistakes, and hopefully the ones I put in there are working. I even did like a 3 cable without separating all 3, like a servo extension. And boy, it's a pain because, but anyway, it's worth it I figured I need to learn this. Other people have done it, and I think very useful skill to have.
Yeah.
I don't know if you've
Very frustrating.
Because-
And there's, oh, I'm saying that DuPont, there's DuPont, these are DuPont, everyone's a little different, every prepper is a little different. You'll get different success depending on which exact connector you use. It's very frustrating.
Yeah, so I bought this kit. I guess I should have given a better picture, but this kit comes with the crimper plus a box of all the things you need, and it has instructions as to like you need to use this last crimper part of the crimper there. The I don't know what to call it, but that one is the one to use, and it shows you how to insert it a little bit inside, not from the outside. Anyway, so it's just this tiny little pamphlet that tells you, and then you just have to practice.
How much did the print cost?
The crimper with the whole box of stuff, I think it was $30. It comes with like
That's not bad.
all the connectors you're going to need for a year, or I don't know, maybe multiple years, with female connector, male connectors, wire, and it also came with what's that? Housings, and this one also came with the another box of those what are they called, the JST connectors. So those you can have the female and the male, and those little white connectors. So you could create those in a robot. I like modular design, and I don't like soldering stuff that I may want to change later. So that's why
I still solder it.
you still solder. I don't want to have to.
In the one time that I did not solder, the connector came out and I didn't know what the problem was until I
Yeah.
troubleshooted.
Like on this modification, I didn't want to solder, and yeah, and I was worried about these wires here being loose,
Yeah,
because
those.
it's just
Those will get
it's
loose.
just these are just DuPont connectors. But what's fascinating or what's interesting is when you print these cases, it leaves a very tight small amount of room here for these pins. And when you put these in that situation, they are solidly in. They will not jump out with the bumping. You have to pull with your hand.
Yeah, they still.
Perhaps,
Yeah.
a bit of advice for you. Do you have a hot glue gun?
Hot glue gun.
Voice of experience would like to recommend that you invest in a.
I do have.
Yeah.
If you use bigger connectors and you get more pins on one connector, it's less likely to come out. So even if you're doing one wire, if you have like one of those sensor boards, use all three. It's a lot.
And also, like when like this table here is a three socket connector.
Yeah.
Some of them are ones, or whenever I can, I use multiple ones.
And as long as the device doesn't move very much, you should be okay.
But like I'm, but I'm telling you,
Some more vacuum. Vacuum container, you'll be okay.
well, yeah, like I said, when you tug on this, you have to pull quite hard because it's wedged in this case. You understand what I
I
mean?
hear you.
In your defense, Jim, I'm using these and I crash my car all over the place and they're not falling out. Because I think they're so light, as long as you get a decent,
No,
have to
right.
load it up.
Oh, yeah. I may use the glue gun, but at this point, it's lucky if I get the project, to do what it's supposed to do without worrying about wires popping out. But I mean, it just is very cool that this combination of having a case and slightly wide DuPont connectors, it wedges pretty good. And then you could glue gun on top of that to really make sure, which sounds like it's a good idea. So then, moving on from there, here's a top view. Now I also bought a powered antenna for the external. So this is the GPS external antenna. I just figured you might as well do it since the board supports it, and you should get better reception, or the best reception possible with it's a 3 volt, I think, and the board supplies the 3 volts for powered, antenna. Now, oh, here, this, anything else I want to show first? Oh, so here are the components. You're probably all familiar, or many of you, with the Raspberry Pi 4B, the main brain, and that's running Linux, Ubuntu Linux, and well, ROS, for the higher level. We won't get into the ROS in this talk. I'm only going to cover the sort of the low level Arduino code or microcontroller code. Here's the Teensy. The Teensy is powered by a micro USB that plugs into the Raspberry Pi, which also communicates that way over serial. So so that all the commands can come from Raspberry Pi to when it's ROS enabled. With just the microcontroller code I initially did, which I'll be showing you, everything runs here, and there's only power coming from that. It also has a battery you can have put in here for time for the clock and that sort of thing. The Teensy, I had this in my shelf for a few years, $30. I bought it and Sergey's using Teensies a lot or somebody, and I'm like, okay, I got to buy a Teensy. And then I'm like, oh, I need it. I want it for this project because it's extremely powerful microcontroller, hundreds of megahertz, clock rate, huge amount of RAM. It's really great. This is and it can handle a lot of peripherals and a lot of I/O. This is the MPU, very inexpensive for your accelerometer, etc. We won't talk too much about that. This is the GPS for more, for the more advanced project I'm doing. I won't be getting into the code for that this time, but that's the main components. And then go back here.
A quick question about your IMU. Have you got the compass working for that one? I never got that working for that chip.
Yeah, in an earlier project I used the compass, not this project. If you go back to I had a little walking robot, the Otto. I used the compass for that because I was having trouble getting the accelerometer, not the accelerometer, the gyroscope. They always have drift, and you're supposed to tune it, keep it stationary. And I was in a hurry, and I didn't want to learn or whatever. And so I'm like, I'm just going to use the compass. And so I set it up with the compass, and I had the robot walk a straight line by, checking the compass direction. So it does work. But it's subject to all the magnetic problems that you get with magnetic. Yeah, magnetometer. But I put it on a wood table, away from everything, and it was able to do something reasonable, walk that straight line, and it would stop and take a measurement and turn. But yeah, I'm putting it in here for the ROS implementation of micro ROS, which is what I'm running on here now. I won't talk too much about that. This is an intro course, so I'm not going to talk much about micro ROS. But micro ROS uses the code I've been given that's available in the Lino robot code base, uses the IMU and has support code and drivers for it. So you hook it up and it publishes an IMU topic in ROS, and that helps the whole system know where it is. So here, I whipped this up last night with the rough, or with the essential wiring, and using the fritzing, which I've always kind of wanted to use and never really used it. So here are the 3 servos that are on board. The ones I added are the pan and the tilt for the camera, and this is the steering that came with the truck. And so, and then very importantly, this here is the receiver, the receiver is this block of connectors, and that's what was under that plastic or rubber connector. This is the real hack to your device, and oh yeah, I'm gonna get into how you, find out what kind of signal you need here. So this is now, in the original, the stock robot you buy, these are connected directly to the steering and directly to to this thing, the ESC, which controls the motor of the robot. But I sort of hacked it and inserted these electronics, this teensy, to now do the control itself, instead of the RF. The RF, when you use your remote control, the signal is coming through these pins here, and then goes to the steering servo, and goes to the motor, ESC. So I'm hacking in, and I still wanted to keep the remote control signal so that I could have a manual mode. So I am able to use the original remote control if the system is in manual mode, and I forward those signals. So you can use it just like the original device. Or if in automatic mode, it's the software takes over and can run the system as it sees fit. And in addition, there's an emergency stop feature where here's the remote control in my picture, my videos here. The Robo-Magellan course and other contests require you to have an emergency stop switch. So in this case, when it's in automatic mode, I have to keep the full throttle on, and if you let go, the robot stops. And so that's why I kind of wanted to use this as a multi-purpose thing. In manual mode, it controls the robot as a normal RC car. And in auto mode, you must hold the switch on for the automatic system to be able to move the car.
So for anyone doesn't have a lot of experience with that, why wouldn't you just do it the opposite way? Why wouldn't you just have a button to press if you want it to stop? Why do you have to hold it down?
Well, they call it I hate to use the term, but the deceased man switch is a way that if if something happens, the car goes out of range, or for whatever other reason, it has to be the other way. For an emergency stop, it has to be loss of the signal rather than gain of the signal or sending the signal. Because what if your signal strength is dead, your batteries die, you're out of range? The robot will keep going if you need to send it a stop signal. This is a keep going unless, this is basically, if you don't receive this keep going signal, stop. That's the concept. So, so that means I have to, on a contest, I have to keep within distance of the remote, or the robot will stop. But in this contest, I'm trying to make the software so that if a child runs in the way of the robot and you stop it, then when you clear the scene and resume, the software must be able to resume without getting confused. So that I'm working on. In ROS, it's going to be an emergency stop topic, so that it will send this topic just in case. I don't know if I need that yet, but I'm going to just publish that because it's easy enough, so that so that the system knows when emergency stop is activated. So it doesn't build up like an acceleration, like, hey, I'm not moving. It must be a really sticky ground, and goes up to full speed. And then when you turn it on again, it zips away or something.
That wouldn't be a simple if-then statement or something like that, if else,
Or
to code that.
yeah, well, I mean, as long as the system knows that there's an emergency stop happening, but right now it's at the microcontroller level. There's no the upper level system does not know it's just been stopped. It doesn't have any idea. It just knows that it's not moving, and then therefore the upper level system might say, put more power in because I'm not moving. It's like in an animal. It's as if you touch a hot stove, and you know how if you're familiar at all with, if you learn biology in high school, whatever, put your hand on a hot stove, there's a signal goes to the brain that you pull away before you're consciously aware. That's what's happening here. If I let go of that, there's no signal going to the receiver and the microcontroller, so it immediately stops. The Raspberry Pi doesn't even know that's happened. And all the upper level coding for navigation is on the Raspberry Pi. So it would have to be told, hey, by the microcontroller, hey, I stopped. So don't ask me to keep going, or don't try to accelerate me.
As long as your TT's working.
Yeah. Well, the teensy code is, the teensy code is always, of course. But if the teensy code stops, then the robot will stop from the hardware point of view, because there'll be no PWM being sent, and the ESC will start blinking, saying, I don't know what's going on, and stop.
Jim, when you're holding down the trigger, that's sending a signal, right?
Yeah.
How do you keep the electronics from fighting, your micro fighting signal? You have a relay or something that breaks it when you're you know what I mean? Because you have two different things. When does the microcontroller know it can fight against the
There's like I said, there's two modes, auto mode and manual mode, which is set by a variable, I'm going to make it an actual physical switch eventually, but right now it's a variable. When it's in manual mode, then all these signals, then the remote acts as a normal remote. It will send the signals to the motors and the steering as normal, as the original product. And when it's in auto mode, then the emergency stop, then this is only used for emergency stop only. Does that answer your question? So there's no conflict there.
Yeah,
It's one or the other.
I think, so there is no physical connection between the receiver and the servos. It always goes through the microcontroller first. So it reads it and then it writes it back out. So
Yeah, there's a
there's
at
the same time.
Yeah, if I didn't make that clear, when it's in manual mode, the microcontroller receives these signals through that RF receiver, and then it's actually through an interrupt code. I'll get into that a little bit. It sees the signal coming in, analyzes it, and then forwards that PWM to the actual motor in manual mode. So I was gonna, people have suggested you can use a hardware electronics, a way to do that, with some NAND and AND gates and whatever. You could just use gate logic. But I thought, oh, well, I may want to capture the steering in the software so that I can use clone training, for instance, in the future, where I drive the robot around the track, all the steering data is captured. I use AI to train it, and so I thought, okay, if the software way doesn't work so well or causes problems, then I could always go back to a gate logic where it simply forwards the signals through a single switch in gate logic. Says it's a select, like on a chip select, so it will say send this or send that. But I haven't done the hardware solution right now. The software one is working fine. So in the future, I might do that as another way. So this is the same thing you looked at. This is a less friendly looking, so I won't. But this is the same as this one. Okay, where I wanted to. Gonna get in, so that's the pictures. Now, I want to show you essentially how these systems work. The car itself uses PWM, pulse width modulation, to control the motors, both the steering and the drive. And so the first thing I did was, although I probably didn't have to, because you look on the internet and it just all matched what other people have found before. But, you know, I did the exercise because I didn't know for sure what the signal widths were and that sort of thing. So I hooked up to an oscilloscope and, you know, plotted it out or got it to go and actually put my probes on the output of those receiver lines that go to steering and go to the ESC. And you can see this one, let's see, where's the name of the file? So here's, well, you can see the names of these. Backwards full, steering full left, steering full right, steering straight. So if we look at these, this is the steering full. What are the names of the file? It doesn't say. Oh, I guess there. Let's not go max screen then. So at the top here, you can see the name of this. This is backwards full, and you can see this width, and then the forwards full. And see the forward full is this much wider one, right? And then neutral is this one. It's in the middle. So backwards is that, forward is that, and neutral is there. So now you kind of know what the width of these this pulse width modulation is. This is essentially taking a digital signal and turning it into an analog for the device to, you know, that device is expecting analog, you know, kind of a work, a certain amount of work signal coming, and that's how you provide that voltage is by changing the width of this digital signal. It's simulating an analog amount of voltage to control the amount. And so, and the same thing with the steering full left, then steering right is the wide one, and then neutral, which is straight, is this one.
So Jim, if you could go back to your full backward slide for a second, there's a very interesting point when you look at this with an oscilloscope. And if you could embiggen that a little bit. So when we talk about traditional servos and sending them servo pulses, those pulses have a certain width, and that width of that pulse means something. Now, looking at Jim's screenshot, if you can move it up just a little teeny bit, or move it up a little bit so we can see the bottom of it, we can see that on your oscilloscope, each square, the width of each square is 250 microseconds. And so what that tells us is that based on how the pulse is framed, this is perfect. We can see that when it's a full backwards, the servo pulse to drive that is 1,000 microseconds.
It says right here, 1.0 microsecond. It's,
That's perfect. And when you look at
this is nano, this is micros, 250 microseconds, 4 times that is milliseconds.
oh, 1 millisecond, okay. And so when you dig into the servo object in Arduino or under the covers and how they do it, that's exactly the only way you communicate with the servo is by sending a pulse between 1 and 2 milliseconds or 1,000 and 2,000 microseconds. The exact ones vary a bit when you get down deep and dirty, maybe as low as 500 and maybe as high as 2,500. But that's a great shot that shows exactly how you communicate with servos just by reading the oscilloscope.
Right. That's yeah. I don't know how many. I don't know if this is kind of you know, if people already know all this, or
Yeah, I'm sorry, I'm just geeking out on the
or
graph.
if
I love
people
graphs.
don't know about this. But yes, I'm trying to you know, do the best I can for the general audience.
Ross also has a question for you. He was wondering what IMU model that you were using. He's working with an MPU 9250 right now.
Yeah, it's a 9250 clone from AliExpress. It's technically it's like 9265, or it's a you can get it for $5 or $3, but it's a 9250 compatible.
Thanks.
Yeah, and I those are very convenient because they're small and they run on very little power. And in fact, the Ross community seems to love them because that one was supported, out the gate by the micro Ross Mino robot code on GitHub. So, yeah, that's that. About the captures.
It was a good one to use because the first time I tried it, I burned it out for somehow or other. And I got another one from Amazon the next day for a couple, whatever it is, $5-10.
Oh yeah, they're very good. They're very inexpensive. Yeah,
And they seem to work. I mean, as far as they talk to the software, I haven't got it verified with doing anything useful, but anyway, thanks.
yeah. So, let's go into this now. Just to show you some of the links from the Traxxas site. You obviously want to know about the electronics, so you can look up the different, obviously the dimensions of the robot will become important later, and then the ESC and what power it can provide. Actually, the ESC isn't as important as whoops, what happened? Oh shoot, did I not? I didn't plug in my power here. This is we call it the DAV tough, ACES tough. See a lot of yeah, it has the 6 gigabyte NVIDIA or whatever. Sorry, so yeah, yes, you want to know, for instance, I wanted to drive some more. This is about hacking, so I wanted to drive more some of my own servos, and so that receiver and the ESC, they provide what's called a battery replacement circuit, BRDC or whatever, and so what that does is it already has like a buck converter that takes down the LiPo battery down to like 6 volts, because that's how the system powers its own servo, its own like steering servo. And so I wanted to connect some more servos, and I was like, do I have to power them with my own battery or not? And then I looked it up, and the official number was like 1 amp for that circuit, but you look up the unofficial and it's 3.5 amps. So it's fine, and it's been tested on that. So, and of course my 9-gram servos, 2 more of my 9-gram servos are not, plus the steering, are not going to tax that too much. So I felt very confident in adding those other 2 servos to the ESC, essentially to this battery replacement. And it's in fact that those pins are made for additional servos. There's 3 channels there with two channel 1 rows, and then a channel 2 row and a channel 3 row, and those are all for RF. This is only a 2-channel RF, so the 3rd row is you can use that for whatever you want, and the 1B, the 2nd row, as well. All right, let me get back online here. Does anybody have any questions while I'm getting back about the hack?
Yeah, I'm gonna lay off until after the John, but I'm very interested in hearing about your experiences with the compass portion of the IMU from within the frame where you mounted it. Because I'm gonna run in the same thing on Alfie, and I'm not sure if I'll get anything useful out of it or not from the base.
Oh, yeah, I mean, my plan right now is I'm not even working with the compass. I'm just gonna use the GPS.
Oh, yeah, okay.
You know, I'm not, going to probably do much with the compass, but eventually, you know, maybe at some point. Uh, okay, here's the, let me get back for one. Because yeah, I would, yeah, that's a whole other, you know, there's a lot more to talk about.
When you pass your input through the microcontroller first, does it create any input delay on the manual mode?
No, yeah, no, not really. Again, that's a good question. What is interesting about this is, okay, I'm back on here. Is that, and I guess, yeah, I've got to quickly move to a little bit of the code part of it. Is the code uses interrupts. The Teensy has many interrupts, the hardware level interrupts. So I found this code online, and I have a bunch of links. I guess I'll share later, but I can show you one or two of them now. But you know, with a hardware interrupt, it's a real-time analysis of this incoming signal and real-time sending out. So there's no noticeable human time delay at all. And
The PWM is going at 100 hertz, which is pretty slow, and the microcontroller is 600 megahertz.
yeah,
So
no
you won't
possible.
say anything
The
there.
Teensy is
Won't
very,
do it.
very powerful. I wouldn't use an Arduino Uno on something like this, probably, but, you know, where's the John? Web links. Yeah, this is the thing I've been talking about, the receiver. And this is where I, you know, plug in my servos for the, well, this is where the steering servo would normally go and the drive motor or the drive signal comes. And what's interesting is the power is actually coming from the ESC into here. So that's, you have, and then so the power comes from the ESC, the 6 volts, and then also the signal goes the other way from here to control the motor itself. But this whole unit is powered from the ESC coming in. So I still have to keep that line in. And the grounds I had to tie. So you have to tie the ground of my battery and their batteries so that the signal will work from the Arduino or from the Teensy. That's an important aspect, ground tying. And let's see, now. Yeah, so I won't, so you look up the specs of this thing and you can, you know, then like I said, I found out this, it certainly already has 4 ports here. So I just put in 2 more servos on the load of this, and they're just small micro servos anyway to move the camera. And yeah, you can use the documentation of the from Traxxas itself to make sure you're working with the electronics safely, and that's something, you know, obviously I did recommend doing that. And yeah, there's different websites. This is the main website, and then I was clicking on electronics. And yeah, and then I won't go too much in it. And then there's the owner's manual. I would look there as well for any info you need about that. And then so yeah, let's move on to the actual code here briefly. So this is I'm using Platform IO within the system of VS Code. And VS Code Platform IO is an alternative to your standard your standard Arduino IDE. And I'm really digging it nowadays because it's got, as Alan will testify, it's got so many nice features for parsing your code as well as the Copilot, and I use Copilot as well, GitHub Copilot. But yeah, the core is here where you can see that now out of what you saw there in those oscilloscope, this is the actual numbers. The neutral PWM is 1500, full forward is 2000, and then reverse is 1000, and full right and full left. And I didn't want to go 100% full left because it makes a sound. It's like, I think that wherever they might have mounted it slightly wrong or small.
Yeah, and they're not exact with servos. So like we want everything to be perfect with 100 is exactly 90 degrees to the left, but between the potentiometer and how it's mounted and how it's glued and imperfections in the components, it's never exact, which is fine for left, right, like when you're just steering it because your closed loop is your eyes, right? You adjust it, but when you talk about robotics and stuff, you're like,
Yeah, well, I'm using the steering as is. I'm not going to replace that, but this in the full system with ROS2 and NAV2, and GPS and IMU, and encoders. I didn't talk about encoders. I don't have them on the wheels. Some of the other guys here do. I will put those on after this contest. I just don't really have time right now for wheel encoders. Like a homemade solution that Justin put together, Brian's nephew. Anyway, but for now, I will rely on those upper level systems to determine where the robot's going and correct the steering in a closed loop through the ROS, basically ROS navigation. So then, this is basically, I just go through the high level, manual mode, auto mode, and to facilitate manual mode, we calculate the throttle, we'll calculate the steering. That's figuring out what the PWM coming in is. And then these other things are like get to steering by like a percent instead of like a percent. 0 to 100 is much kind of easier to deal with in most cases than the PWM signal. I don't want to think about that. But you can see this is a traditional Arduino setup and loop functions. And you can see it's setting up the, this is the e-stop pin. And then that's like critical, as I said. And then there's the throttle and the steering, which are both using the regular servo class, which the servo class puts out the PWM that I need, really, or even though it's going into one of them actually goes to a servo, the other one goes to the ESC, which is then converting that to the right voltage to the actual motor. Well, it's it's the velocity, it's the control of the motor. So that's, you can use the servo class in Arduino.
Oh, I think we just lost the camera.
Walter, I think your foot just disconnected the.
Yeah, I see.
Let me know if you can, if this is too small still, or can you see, can the people online?
Yeah, it's really.
And then, when this system is running on the Teensy, this code all runs on the Teensy. So the Teensy has an LED, and it's nice to use that LED to tell you what's happening with blinks or whatever. So you can set it to blink for error codes or for when things are working normally. And so that's kind of a good use of this. So I have it flash every 500 milliseconds. And that's using a timer, and which is available to you just through the libraries. So this program uses the servo library. It's also, that's like the main one, I think. And in the main loop here, we're going to, support manual mode and auto mode. And so the auto mode, so now this one was set up, this code was set up to be for testing with the keyboard. You can control all what's going on. So that's why I have this whole, you type R to turn right, L to start turning left and forward. And each of these like increases increases the throttle, decreases the throttle, it increases the leftness or the rightness, which is really increasing, decreasing, and then stop. And for steering, S is to steering straight, and then neutral throttle is N, whatever, it's whatever you want. And then a way to switch between manual mode. Manual mode then will just use the remote control like a normal, like the original product. And auto mode will, in auto mode, these letters do something. In manual mode, those letters don't do anything. Only the actual remote in your hand controls the robot. And so, as I said before, I won't get too much into this code, but the key thing is that there's an interrupt I think you saw that at the beginning here. The interrupt's installed so that right here, interrupt for throttle pin is always present. So this allows when you actually are using in manual mode, as soon as the signal changes, basically as soon as there's a change in that, if you're looking at an oscilloscope, as soon as the voltage goes up or down, this routine gets called, or a routine gets called calc throttle, and that's a hardware interrupt. So the Teensy is looking at 400 megahertz at that signal coming in, and it's only 100 times a second anyway. So as soon as that thing goes up or down, this routine is called, and therefore then I measure it. I'm measuring the length. So it goes up, I start a timer, and it goes down, I stop. So I've measured the width of that, and then I forward that width. And the same happens for steering. But I only need one interrupt, so you can do both of them. Or actually, no, I think anyway. But so that's any questions about this? Is just a quick review of now. There's what's nice about, or what's also to point out is that there are good resources online that help me get going on this. And that's where I started. I did modify from there, but can't remember if I have the links.
Oh, hey, Jim, I must have missed it, but what is it that triggers between manual mode and auto mode?
Well, in this initial script, this initial code that I did to test the system, it's you use a keyboard on the, use a keyboard and, through your.
Oh, no, but I mean like on the remote, because that's only a 2-channel remote. How do you trigger that between auto and?
But to change between auto and manual, it's not on the remote.
When it sends the signal from here, then it knows to go into manual mode?
No, manual mode is through other ways. It's not through here. It's either through the keyboard or through a ROS.
I see. You still have the laptop override.
Yeah, I have a laptop.
Okay, not the remote override. Okay.
There's no
There's no trigger on the button on the remote to.
No. What I'm thinking of adding is a physical switch on the robot to switch, you know, because when if I'm at Robo Games, I will drive it around manually to get it in position.
Mhm.
And then I go up to the robot and switch to auto, and that also tells it to start the race. So I'm going to
Right.
add a button on the robot, so I don't have to go in the laptop. And
Yeah, because that was what I was thinking, laptop would be too inconvenient, so.
it's kind of inconvenient.
Yeah, all right,
But yeah, I don't have both these channels are in use, one for
Right.
steering, one for throttle.
yeah. that's-
So there's no, if I had a third channel, if I get a new remote and then I redesign, I
I could
could
easily swap it, they have like 6-channel remotes and you can do multiple,
Yeah, but my,
super easy to change.
I don't, I haven't got into that. My receiver only has 3 channels. So, and
I gave a presentation to the radio.
I
master,
should
but
do
they-
the,
Yeah, that was a good one, yeah.
15.
15.
If you go to change,
Oh,
you
yeah.
change both at the same time, change your receiver
Oh,
and
yeah.
your
well,
controller at the same time.
okay, yeah, but one cheap thing I could do is just buy an upgrade to this that has 3.
That's what I always do.
And my thing has
Yeah.
already got 3 channels on the
Yeah,
receiver. So that I don't want to have, yeah, so I wouldn't have to replace the receiver
Yeah,
on
even
the,
like a 6-channel is like $35. They're not expensive, but his is like amazing. He's like the top of the.
yeah, I mean, I want something, of course, that fits under the hood of that in the same,
Yeah,
footprint as the old one. But, you know, yeah, I would at least upgrade to a 3-channel. And if there's a way to upgrade, maybe I could upgrade to a 6. in
that's
that
what I
same
did.
thing.
Actually, last night I did that. I swapped one from 2-channel, the Traxxas, to the 6-channel.
Yeah,
Last night I did
yeah,
that,
so
yeah.
I have to you buy a new one of these and
It
a
comes
new-
with the receiver, yeah.
Oh, it's a one
It
one
comes-
price.
This is a package, yeah.
Yeah, so that's an idea I will probably take on,
Yeah.
definitely late at a point.
You could use the aircraft style ones if you wanted to, right?
Well, that's what.
It can, but it's kind of hard to control a truck with the RC. I've done that too, and I don't like it. Okay, the pistol is the best.
I got a van controller, so it's got, but it's got 15 channels, all the switches everywhere, but it uses a different protocol, so you have to deal with the other protocol.
Yeah, but I've done it both, and I prefer the pistol for an RC truck like this.
Yeah, I've never used one.
Yes, that's, you know, a lot of these guys here have, more experience than me in this. I'm kind of fresh into the RC car modification. So yeah, I can use advice, on the future. Right now, it's kind of I'm getting the basic thing implemented.
Oh, yeah, one more thing, like the remote that he was showing, some of them provide feedback on like the battery level and everything, right on the remotes, so you
Yeah.
can see what's going on with your truck itself. It's very nice.
I'm always wondering if my battery.
Yeah, that's another thing you can
Oh, here it is.
look at it right there.
Yeah, so you just have to set that up on both ends and you can, yeah, so this project that I'm working on has it's a beginning of a long-term project that has many upgrade paths. Like they're talking about even the low level, and then of course the raw side is just, there's so much, capability there that you can add. So this guy, Eric Maggard, produced a 4-part series of building an autonomous car. I used this for part of mine. In fact, that's where I started with, and it's very helpful. And he got into the signal measurement. I mean, I could write one of these. I should maybe write something myself for my experiences after doing all this. And
You
so,
definitely should.
because I kind of he was using ROS 1 and, some slightly older stuff, but some of his code, I ended up using in that code I just showed you. And he explains how to do that, that interrupt, or I guess
Right.
mainly the code explains
Yeah,
itself.
that's a good one to have there. Like.
But yeah, here's the idea is, this is the delay, by the way, between when the signal comes in and when it's going out. You can see it's in a millisecond, very, very quickly does the input from the controller, and then it's measured, and then the output from the teensy. And so there's almost no delay. And so, yeah, that's how we're doing. Okay, so, so that's some good resources. I'll post some more of those. If they aren't posted by Alan or somebody. And, so yeah, anybody have any questions about any of this?
So you're using Micros to facilitate the communication between your Raspberry Pi and your TeamSpeak, right?
This, yeah, exactly, in the other code.
Okay. And so on your RC car, basically you've got like forward, backwards, and steering. That's what you're trying to control. What ROS messages are you using to facilitate that? Are you using Twist or as a custom message format?
Well, command velocity is the name one. It's command velocity has,
Is
and
that a standard?
that's standard ROS message. CMDVEL, is what the, in fact, I'll do it, if I have a chance, sign me up for, if my router is working here, I will do a demo of, controlling the robot from ROS. Manual control. So essentially it's a it uses command velocity, and inside command velocity comes with a twist and, which is an angular velocity and linear velocity. Both of those.
So that is one component of it.
Yeah, they're all, command velocity is the topic. And inside there's a message for twist and a message for, the velocity of linear and angular. And so if I am able to get it running later, I'll show you this GUI that they have called RTT steering, which lets you use sliders and adjust the throttle and the angular velocity. And then your robot will drive.